Let's discuss how to find the rate of evaporation for a three-component system. For our three-component system, we'll have a Stefan tube, and the Stefan tube will have a covering above, a mesh covering, so that there's no pressure-driven flow. Inside, we have our acetone and our methanol, and above the Stefan-driven tube, we have our air flowing, our N2. The thickness right here is equal to 0.24 meters. And we also have the information about each component, so how much of the vapor is of each. So Y1, we'll say that acetone is 1, methanol is 2, and air is the third component. So for Y1, that's going to be 0.318. Y2 is 0.528. And so Y3 is equal to 0.153. The composition of the air is 0.13 because our entire vapor should be equal to 1, right? All of our components should be equal to 1 in percentage. We also have a pressure that is not 99.4 pascals and a constant temperature of 328.5 Kelvin. This is actually kilopascals, not pascals. With this information, we're also given our diffusion coefficients for our acetone to our methanol, and that's going to be 8.48 meters squared per second. Going to be kilopascals. We also know our diffusion coefficients, so let's put all our information together. Our diffusion coefficients from 1 to 2, which is our acetone and our methanol, is equal to 8.48 millimeters squared per second, and then have from 1 to 3, our acetone to our air, that's equal to 13.72 millimeters squared per second, and from the methanol to the air, which is equal to 19.91 millimeters squared. From here, we can use our Stefan-Maxwell equation to determine the rate of evaporation, or the first step at least in determining the rate of evaporation. So we have our Stefan-Maxwell equation. And this tells us that our driving force of I is equal to the change in our mole fraction of I divided by the change in distance z. And this is also equal to the sum with respect to J of our mole fraction of I multiplied by the molar flux of J minus the mole fraction of J multiplied by the mole flux of I, and that's all over the concentration multiplied by the diffusion coefficient of I, J. We can find the driving force of our acetone and our methanol. We don't find it for air because we can determine that using the acetone and methanol, since the idea that our mole fraction of 1 plus our mole fraction of 2 plus our mole fraction of 3 equals 1 exists. So let's do the driving force of our acetone, which is 1. That's going to equal our mole fraction of 1 multiplied by our molar flux of 2. And again, 1 is acetone, 2 is methanol, but I'm not going to say that because that's a lot of words. Minus our mole fraction of 2 times our molar flux of 1 all over our concentration multiplied by our diffusion coefficient of 1, 2. Now from here, we're going to subtract our mole fraction of 1 again, multiplied by our molar flux of 3 this time, minus mole fraction of 3 multiplied by our molar flux of 1 all over the concentration and diffusion coefficient of 1 to 3. This is for acetone. Let's label that acetone. And we'll have our methanol up next. I'm just talking and thinking, so don't always spell things right. So then we have our driving force for 2 is equal to mole fraction of 2 multiplied by our molar flux of 1 minus our mole fraction of 1 multiplied by our molar flux of 2, our concentration multiplied by our diffusion coefficient of 2, 1, minus mole fraction of 2 multiplied by our molar flux of 3 minus mole fraction of 3 multiplied by our molar flux of 2 over our concentration multiplied by the diffusion coefficient of 2, 3. You may notice that I'm missing a part of this equation, and that would be that we would add something along the lines of y1 n1 minus y1 n1 again, right? So you've asked down 2 times, but that's just going to cancel out and become 0, so we don't add that in there. There are a couple variables in the Stefan-Maxwell equations that we have created here that we don't know. One including the concentration, one being the distance, z, and one being the molar flux, which we'll calculate later. For our concentration, it's important to know that our concentration is equal to the pressure over our constant multiplied by our temperature, and that's for vapor. So we're going to move on from that. That can be solved in Excel, which will be solved later. And now for our z, we have to think about the thickness, right? So z is distance, and our thickness is how far or how much distance there is. Let's create a new variable, n, and this is going to be a scaled variable. So n is scaled, and we want it scaled so that we can go from 0 to 1 instead of 0 to 0.24 meters or whatever. So that means that n is equal to z divided by the thickness. And that'll be out of 1. So the moment that z gets to 0.24, it equals 1, right? Our n equals 1. And we can use that, and we can say that our change in z is equal to our change in n multiplied by our thickness, since our change in n equals change in z divided by our thickness. So now we'll substitute n in for dc, and we find that the change in our molar fraction of I divided by the change in n is equal to the change in our molar fraction of I divided by the change in z multiplied by our change in z over our change in n. Let's use that identity and substitute it into our Stefan-Maxwell equations. You should understand that these equations that we just derived for, or just created for methanol and acetone, they are also equal to the change in their molar fraction, so this would be the molar fraction of 2 divided by the change in distance, and this one would be the molar fraction of 1 divided by their change in distance. So I'm going to take it over these equations over here to create some more room for us. And we'll find that this will substitute in this identity, this part of the equation right here, and we'll get the change in y1 over the change in z, or distance, multiplied by the change in z over the change in n, equals the change in z over the change in n multiplied by this entire part of the equation. So we'll just move that over there. Same goes for the methanol, but we'll do that in a second. And now we can cancel out some units, cancel out both our changes in z right there, and we can also understand that this change in z over the change in n, if you rearrange this equation right here, or this equation right here, you'll find that our thickness equals the change in z over the change in n. So this is actually equal to the thickness. And our final equation is our change in molar fraction of 1 divided by our change in n equals the thickness multiplied by this entire section of the problem. And now it's the exact same thing for our methanol, so, but instead it's the change in molar fraction of 2 divided by the change in n equals the thickness multiplied by this part of the equation. Right? So now we found that our driving force of 2 and our driving force of 1 are equal to the change in our molar fraction divided by the change in n, and that is equal to the thickness multiplied by the sum of the mole fractions times the molar fluxes divided by the concentration and the diffusion coefficient. So from here, before we move to Excel for our rate of evaporation, we have to make an assumption about what our molar flux of the acetone and the methanol might be. So let's take our equation and pull it to the side. You don't want to pull it that far to the side. And look at it a little close. We're going to assume that this is about equal to 1, right? Our scalar value is around 1. From here, we'll draw out, this is about equal to 1. That our molar fraction of 1 multiplied by, we'll have our molar fraction of 1 multiplied by our thickness and our molar flux of 2 over our concentration and our diffusion coefficient of 1 to 2 minus our molar fraction of methanol times our thickness, molar flux of 1 over our concentration of 2 plus our mole fraction of 1, thickness, molar flux of 3, our air, divided by our concentration and our diffusion coefficient of 1 to 3. From here, subtract our mole fraction of our air, our thickness, our molar flux of 1 divided by our concentration and our diffusion coefficient of 1 to 3. 1 to 3. We can cancel this part of the equation out because our molar flux of 3 is actually equal to 0. There's nothing going on, right? It just reacts with the molar flux of, or the flux of whatever's going on in that part of the tube. And we also know, or we don't know, but we're going to make a couple other assumptions. One assumption that we're going to make is that our mole fractions of 2 and 3 of the methanol in the air are somewhat equivalent to 1, where we are in the tube. So I'm going to solve for N2. And N2 is going to be equal to our concentration and our diffusion coefficient of 1 to 2 divided by our thickness. And as we saw before, our concentration is equal to P over RT. So we substitute that in and we get P, diffusion coefficient 1 to 2 over RT. And our thickness is equal to our molar flux of 2. Now let's plug in the numbers that we have. And we're going to make some extreme rounding decisions. Why? Because we're engineers. That's what we do, right? So we have our pressure, and our pressure is 99.4 kilopascals. Why would you do that when you could just do 100 kilopascals? So we have 100 kilopascals multiplied by our diffusion coefficient of 1 to 2, which is 8.98, but it's not really, it's also 10. Times 10 to the negative fifth, because it's in millimeters and not meters squared per second. And that is over R, which is 8.314. We'll just say it's 10 again. Multiplied by our temperature, which is what, 328.5. So that's just going to be 300. I'm going to round down this time. Finally, our thickness, which is 0.24, but that's just 0.2 meters. And our 10 is actually in, we'll write the units, I forgot, joules per mole Kelvin. If you multiply that out, that equals 1 over 600. Now this is around somewhat true for both the molar flux of N1, or molar flux of our component 1, which is acetone, and our molar flux of our second component, which is methanol. So it's true for both of those. And we know that because they're going to be around the same at that point, right? They've both gotten there. So we're going to move on to Excel from here. Put almost all of the variables into the Excel already. We have our mole fractions, our diffusion coefficients, pressure, temperature, constant. We still need our concentration. We have our D, which is 0.24, and we still need our change in C. So we'll say as we know, our concentration is equal to P over RT. So we have our P divided by, remember to put this in parentheses, our T multiplied by our R. and that is our concentration. And then for our change in Z, we're going to do something, we're going to do 0.24 divided by 1,000, so we can have 1,000 variables. So I'm going to come over here and I'm going to create area for our solver. So we'll have our Z, our mole fraction of 1, 1 and 1, our mole fraction of component 2, our mole fraction of component 3, and then we'll have our mole fraction of 1 divided by change in mole fraction of 1 divided by our change in that variable n. And another thing we want to add is the fact that our mole flux of 1 and 2, we estimated to be, where's that no one? Mole flux of 1 and the molar flux of 2. We estimated to be around 1 divided by 600. We don't want that to be it. 1 divided by 600, and it goes to the same for this one. It goes 1 divided by 600. All right, wonderful. So we have values ranging from 0 all the way until 1,000. And for our Z value, that's going to be equal to whatever values in this column multiplied. Is that what I want? Whatever values in this column multiplied by our change in Z. So if we drag that all the way down to 1,000, here's a lot of values. Keep going, keep going. There we go. Oh, hello? Excuse me? Oh, shoot, I did the wrong number. You want to multiply that by this, right? And now we drag it down. There we go. It should, at 1,000, it should be 0.24. That's odd. What do I have here? Do I still have that? Okay. Was that there? And then right here. I see what the problem is, right? You have to make sure that you have dollar signs in front of that so it stays constant. Now, now this should be correct. All right, perfect. Yep, 0.24. And our y1 value is equal to, it's equal to this. Our y2 value equals that. And our y3 value is equal to that. And I put in the wrong numbers. Great. There we go. For our change in y1, our change in the mole fraction of 1 divided by our change in n, you have to understand that there's math involved, right? We already have that math that we just derived. This is equal to our distance multiplied by our mole fraction, 1 multiplied by our n2, and that's gonna be, you're gonna have our mole fraction of 2 multiplied by our mole flux of 1 subtracted from that, and divide this whole part by our concentration multiplied by our diffusion coefficient of 1 to 2. So that's the first part of that equation. No, that's not what I want. That's okay. I know. So I'm going to put in a couple more parentheses. So it doesn't get mad at me yet. We have that part of the equation. And from here, we'll add negative mole fraction of 3, or component 3, multiplied by n1. And that is divided by our concentration once again. Concentration once again. Hello? For concentration, thank you, multiplied by the diffusion coefficient of 1 to 3. because that's what we're doing. We're going from component 1 to component 3. Next, we can do a change in our mole fraction of our methanol divided by change in N. And that's going to be a similar concept. We're going to have our, but this time we're going to be using Y2. So we're going to have our distance multiplied by a couple parentheses in there. Mole fraction of 2 times N1 minus mole fraction of 1 times N2. And this is divided by our concentration times diffusion coefficient of 1 to 2. From here, add to it negative molar fraction of our air multiplied by molar flux of 1. And that is going to be divided by concentration. I put that in parentheses there. Our concentration times our diffusion coefficient from 2 to 3. I'm going to make sure everything's all right within these equations. So that has parentheses, that has parentheses. We'll put parentheses. Maybe. So you also don't have to multiply this equation by the distance because you're going to do that later with Euler's equation. So just don't add that to your problem. These should be what your each cell should look like. Okay. So now we're going to find the mole fraction. That's going to be using Euler's equation, where you've been, plus your derivative right there multiplied by distance you're going. And it should be approximately the same for this one where you've been. Plus your derivative multiplied by where you're going. And this is going to be equal to 1 minus the mole fraction minus your other mole fraction. No, no. Minus your other mole fraction. There we go. There we go. Okay. So what I am going to do is I'm going to make sure that there's correct dollar signs everywhere they need to be so that the constants are constant. 1 second. All right. H3. That should stay there. B12. B12 is going to be our concentration. It should stay the same. Multiplied by our diffusion coefficient. That should also stay the same. And then we have I3. That can be different. B17. Oh, that should stay the same. Divided by our concentration once again and our diffusion coefficient. All right, perfect. It's going to be the same number, and I'm going to do the same here. Should be dollar signs in roughly the same places. Yeah. Our concentration and our diffusion coefficient are always going to remain the same. The only thing that's changing is the molar fraction, if you notice. It should also stay the same. Perfect, and I'm going to do the same for these, so those can all change, that's fine. Now for this one, our initial changes. That changes as well, but the distance does not. So make sure there's dollar signs right there. There we go. All right, so all my constants should remain constant, and now drag these down. And then from here. Look at that. Look at that. That's beautiful. Let's scroll all the way down. Bam. So I actually messed up a little. I put the diffusion coefficient as a different number than this. And I changed that, and now all these numbers should be correct. But if we scroll all the way down to 1,000, you'll see that the mole fractions for our component 1 and our component 2 are not equal to 0, and that's what we're looking for. We're looking for a value that's equal to 0, and we're looking for our third component to be equal to 1. So in order to figure out what that is, we can use a solver method, and we'll have our y1 at position D and our y2 at position B. And those are equal to G of 1003 and H of 1003. There goes our number, and then we also want to take the sum square of each. This will give us a number. So this is our sum square. From here, we'll use a solver. So this solver will help us find the correct values for our N1 and our N2 values, a molar flux of 1 and 2, in order to figure out how to get our mole fractions of 1 and 2 to be 0 at the 0.24 meters. So here's our solver, and we'll have it. We want the sum squared to be as close to 0 as possible, and we want, so minimum, and we want to change the variables of these two cells. And if we solve, all right, that's good. That's exactly what we want. So now here we have our final, well, here you can see that these values are extremely close to 1. And here we have our final values for our molar flux of 1 and our molar flux of 2. This might be a little, I think those are fine, yeah. We scroll all the way down, you'll see that our mole fraction for our air is almost 1, which is perfect. Scrolling all back up, you'll see our mole flux for our component 1 and our component 2. And if we compare that to our original mole flux that we estimated, you'll get we'll have our theoretical value divided by our actual value for both of those problems. Our theoretical value divided by our actual value. So for our component 1, our acetone, it was pretty accurate. It was within what we wanted. And then for component 2, it's a little further away from what we estimated, but it's still pretty close. So what we can learn from this is that the scalar value, scaling up using a scalar model in which we took our distance that we traveled, divided it by that thickness in order to have a more manageable number. As you can see over here and over here, right? We were able to estimate a value with that Stefan-Maxwell equation, that 1 divided by 600, in order to somewhat find the molar flux of both our first component and our second component, which is kind of crazy for a solver to have to use all of this information in order to find that. And so overall, our Stefan-Maxwell equation is pretty good at finding our molar flux for our component 1 and component 2 if you're trying to do it by hand.